Hello Chem 1B, this is Chapter 19, Lecture Video 1, and Chapter 19 is going to be about electrochemistry, which is really the chemistry of batteries and how electricity works in a chemical reaction, how we can use chemical reactions to give us electrical power. It's kind of neat. First, we're going to do a couple review slides. Most of this lecture is going to be a review. So, oxidation numbers. These are things that you should definitely have covered in Chem 1A. So just to kind of quickly review that, to keep track of electron movements in redox reactions, which is kind of what batteries and electrochemistry is all about, we assign oxidation numbers to each element, and we treat all interactions as ionic and assign electrons to give the most electronegative element its usual charge. The sum of all the oxidation numbers within an ion or a molecule has to add up to the charge on that thing. So if it's a neutral molecule, it has to add up to 0, and if it's an ion, it adds up to the charge on that ion. All of that should have been reviewed. A couple rules about oxidation numbers are that all pure elements in their standard state have an oxidation number of 0. And monoatomic ions like S2 minus, the oxidation number is whatever the charge is, or Na plus, the oxidation number is whatever the charge is on those things. A little bit more in depth, hydrogen is always +1 unless attached to a metal, and then it's -1. This is a very rare situation. Most of the time you're not going to need to worry about it. Pretty much hydrogen is almost always +1. Fluorine is always -1 if it's in a compound. If it's by itself, then it's 0. See the first bullet point in this slide. And oxygen is almost always 2- unless in O2, then it's 0. But there's a couple other issues. If it's attached to fluorine or if it's attached to itself, then with fluorine, we don't know what it is. We have to figure that out. If it's attached to itself, both O's have a -1 charge. This is like peroxide. And so these are some of the main rules that you need to know. Other halogens are pretty much always -1 unless they're attached to either fluorine or oxygen or another halogen, and in which case we don't know what their oxidation number is. We'd have to solve for it. So let's do an example. And I'm only doing one because this is completely review and you should know it. So if you don't remember it, then go back over your Chem 1A notes, hopefully, or read the textbook. We want to find what the oxidation number of sulfur is in HSO4-. So we know hydrogen's oxidation number is +1, right? Because in this compound, it's a +1 charge. Oxygen here, -2. So we know each oxygen has a -2 oxidation number. And I know all the oxidation numbers in the compound have to add up to -1 because that's the charge on the thing. So I know hydrogen plus sulfur plus 4 times O has to equal -1. Now each one of these are the oxidation numbers I need to deal with. Now this 4 is because there are 4 oxygens in hydrogen sulfate. So if we break this down, we have +1, right, from hydrogen, plus whatever sulfur's is, plus -2 times 4, oxidation number of oxygen, has to add up to -1. And in this case, that can simplify to S plus -7 equals -1. Or in other words, sulfur is equal to +6. And that is my oxidation number on sulfur in this compound. And that's how we would do this for elements that we don't have a rule for. It's very important that you re-go over this, re-go over the rules, because a lot of this is going to be important to pretty much everything in electrochemistry, which is what this chapter is all about. Some other review type ideas, redox reactions occur when we have something being oxidized and something being reduced. Now, the oxidation number of something, two things really, in our redox reaction, oxidation reduction reactions, are going to change. The oxidation numbers will change. Now, one of them will go up and one will go down. The thing that was oxidized, its oxidation number is going to increase or get larger. The thing that is reduced, its oxidation number is getting smaller. So if we look at an example here, Here's a redox reaction. If we look at the oxidation number of Zn, it's 0 because it's an element in its standard state. And for H+, it's +1. Now there are two H pluses, each with a +1 oxidation number there, because it's a monoatomic ion, which means its charge is simply its oxidation number. Zn2+ over here is just an oxidation number of 2+, and since H2 is an element in its standard state, its oxidation number is 0. Now from this, we can tell, and this is, to be honest, the easiest possible example, we can tell what was reduced and what was oxidized. Now, when we're asked what was reduced and what was oxidized, we're always only referring to the reactants because they're the things that were oxidized or were reduced. The were means before, past tense. This is the after, right? We don't really care about these when asked about what's reduced, what's oxidized. We only care about the reactants. Now, I can tell that Zn's oxidation number went from 0 to 2+. This tells me that Zn was oxidized. At the same time, H+ went from +1 to 0. That's a reduction. So H+ was reduced. And again, this should all be reviewed from Chem 1A. All right, so just kind of going back over what we just did, we determined our oxidation numbers for everything in the reaction. Zinc solid was 0 on the reactant side, and then went to 2+ on the product side, making it oxidized. Right, we can see that here, and then hydrogen was a +1 oxidation number, went to a 0 oxidation number, and therefore was reduced. Now, I always like to say that whoever came up with all the vocabulary for chemistry was like totally just hated students. And I think this is my biggest proof for this, and that's the words oxidizing agent and reducing agent. So when H+ causes zinc to be oxidized, right, this is being reduced, the H+. But when we put it with zinc solid, it causes the zinc solid to be oxidized. Because of this, it's actually H+ that's our oxidizing agent, which is kind of funky because while it's the oxidizing agent, it's the thing that was reduced. The opposite is true as well, right? So if we think about Zn solid causes H+ to be reduced because it's going to be oxidized. It's causing the other one to be reduced, though. This makes Zn solid our reducing agent, right? So again, this guy is my reducing agent. Basically, anytime you see the word agent, I need you to think exactly the opposite of the word that comes before it. Oxidizing agent was the thing that was reduced. Reducing agent is the thing that was oxidized in your reaction. And I know how complicated that can kind of sound, but hopefully it makes some sense. Again, this was primarily review from Chem 1A. If you have any questions, please let me know via email or a discussion session.